Nuclear fusion reactions are the source of the impressive amount of energy emitted by stars and produce most of the elements in the universe. In fact, most of the atoms in our body, basically everything except hydrogen, were produced in stars before the solar system even existed. But how do we measure the nuclear processes that power stars? Have you ever wondered why there's much more iron than gold on Earth? Well, to understand that, we need to know all about the properties of atomic nuclei and the multitude of nuclear reactions happening at different stages of stellar evolution. In particular, for each reaction, we need to know how many nuclear fusion events happen every second in a star of a given temperature. To do so, scientists try to reproduce stellar fusion reactions in the laboratory. In our labs, nuclear reactions are reproduced using particle accelerators. Here's how a standard experiment works. An accelerator produces a beam of a certain type of particles with a defined energy. The beam is then sent to a target, and the collision of projectiles and targets will eventually give rise to a fusion event. The products of nuclear fusion, either particles or photons, are then captured, identified, and counted using proper detectors, acting like cameras. If you think it's so simple you can build a laboratory in your garage, slow down a second. Studying nuclear reactions in laboratories on Earth is actually very challenging. In the previous Astronuclear Nibbles video, we learned that the Sun and all stars shine thanks to a quantum physics phenomenon called tunneling that allows two nuclei to overcome electrostatic repulsion and get close enough to fuse. The probability of quantum tunneling to happen is very low. For example, tunneling between two protons in the Sun will only happen in 1 in a billion collisions, and the tunneling probability becomes even smaller if the nuclear reaction involves heavier elements like carbon or oxygen. Therefore, to have a detectable number of fusion events in our experiments, accelerators need to provide very intense beams with billion to trillion particles per second, and detectors should be able to collect most of the reaction products. To make things even more challenging, the signal from a fusion reaction needs to be distinguished from background signals produced in the detectors. To understand the effect of background, imagine you had to hear my voice on a construction site. Well, nuclear physics experiments are not usually performed in noisy environments, but still, background signals can have multiple sources. For example, they can be produced by the interaction of the projectiles with contaminants in the target or surrounding materials. For this reason, targets and equipment are designed to be as clean as possible. Other sources of background are of environmental origin. Radioactive elements are naturally present on the Earth's surface, and they continuously produce photons and other particles. For example, in this apple, there's about 10 radioactive decays per second. Moreover, our planet is constantly bombarded by the so-called cosmic ray shower, produced by highly energetic particles coming from outer space. About 20,000 of such particles crossed my body since the beginning of this video. Over the years, scientists have developed a variety of clever solutions to study stellar fusion in the lab. And when the fusion probability is just too low, nuclear physics theory comes to the rescue. Modern experiments use advanced detectors to exclude background signals or indirect methods to work around the electrostatic repulsion between nuclei. I do experiments at Gran Sasso Underground Laboratories in Italy. The lab is built underneath a mountain and uses rocks to shield experiments from the cosmic shower. Yes, you heard right. Sometimes we need to go underground to study the sky. But if you rather keep looking at the sky and you'd like to know how the very first elements were formed after the Big Bang, get ready to travel back in time with the next episode of Astronuclear Nibbles.